Okay, so we are going to talk about rotation matrices. We'll do two exercises, and the exercises will not be on the specific rotation matrix, namely how we present it as a matrix and how we take, for example, the eigenvalues and how we use cosinus and sinus. No, we will just use the properties of the fact that they rotate the matrix and use it. For example, if it rotates it 100 degrees, then I know that if I apply the transformation three times, I get 360 degrees, so I get back to the original vector, so it behaves after three rotation, for example, like a unitary matrix. So we'll use those properties of the rotation matrix, and this is the main thing. So let's look at two exercises. So I'll just make it so that you can be able to see it. Yes, I think you can now see this. This is exactly what I want. Yes, so great. So the first question will be that we have a transformation from R2 to R2 transformation. Look, it's 120 degrees counterclockwise around the origin. I also know about this transformation. This is the first thing. The second thing that I know is that we have a polynomial um, that we define, which is this one. Now the question asks, if I apply the transformation to this polynomial for x and y, will I get again the vector x and y? Namely, I won't change it. This is the question. Now, again, look, we have a 120 degrees of counterclockwise around the origin. Therefore, if I apply three times the transformation, I will get to the original, because I'll do the whole circle, so I'll get to the original vector. This means that if I apply the transformation three times, namely 2t to the power of 3, I will get to the identity matrix, and I will use it because, for example, when I will apply the transformation to this polynomial, I will get, instead of this one, this is t to the power of 3, I will get I. Now also I can look on t to the power of 4 as 2 to the power of 3 times t. So I can say that this is I times t. This is the same for this one. This one is like t to the power of 3 times t to the power of 4, and t to the power of 4 is t to the power of 3 times t, right? So again, I will use it, we'll see it. Okay, so let's start. Again, t is the rotation 120 degrees. Take it three times, you will get to the I, so t to the power 3 is I. This is the first step. Second step, let's simplify the polynomial. So when we apply the transformation to the polynomial, we get this one. Now let's apply t to the power 3 to the I, so we will divide them. For example, t to the power of 7, I can say that this is t to the power of this one, which is just give me t, right? Because you can apply t to the power of 3t times and then t, so I get I two times, which is I, and then I get t. So instead of t to the power of 7, I get you'll get t. T to the power of 4, the same idea. It's like t to the power of 3 times t to the power of 1. Now, t to the power of 3, we said that this is I, so this is I times t, which is t. Now, the last one is t to the power of 3, which is I, because this is the definition we just defined. So I can simplify this polynomial to be, when I substitute t, to be like this, which is just the identity matrix in the end. So of course, if I'll do this identity matrix polynomial with substitute the t for, and I apply the identity matrix on a vector, I will get the vector itself. So the saying that applying the t to this polynomial takes vector and stay with the same vector is correct. So this statement is correct. Okay. This is the first thing about in the exercise about rotation matrices. Now we'll get to the second one. And again, this is a statement which says, again, we have a transformation from R2 to R2. This now is the reflection with respect to x, meaning that it takes a vector and transform its y coordinate from y to minus y. And again, we have a polynomial and we are asked if using this transformation on the polynomial will transform a vector into x and minus 3y. Now, again, we'll use the same technique. You know that if I apply once, I'll get x minus y, and if I apply twice, I'll get back from this to the original vector. Therefore, taking this transformation and raise it to the power of 2 will give me, again, the identity matrix. Now, therefore, t to the power of 2 equals I. Again, I will use it in this polynomial. We'll substitute t for the transformation t, and again use this technique of t to the power of 2 equals I and simplify the polynomial. Let's see how it goes. Here's the polynomial. Here's the polynomial when I substitute t. Now, take t to the power of 2 equals I and simplify the polynomial. This I stays I, this t stays t, but t to the power of 3, I can say that t to the power of 2 times t. Now, t to the power of 2, we said that is I, so it's I times t, which is t. Therefore, we are getting for the polynomial substituting t, we are getting t plus t minus I, which is 2t minus I. Now, using this on a vector gives me 2t minus I times the vector. Now, let's just multiply. So 2t vector minus I vector. Of course, the I vector stays as a vector, but t on a vector is this. Now multiply this by 2, you will get minus 2y, which is, and 2x, which is this one. Now substitute x, y from this, and you will get 2x minus x for the x part and minus 2y minus y for the y part. So we are getting the vector x, comma, minus 3y. So this is true. The statement is correct. Taking this rotation transformation t and applying to the polynomial we got really takes a vector xy and transform it into x, comma, minus 3y. So this was 2 exercises on rotation matrices. On the idea, we didn't get into, again, into the matrix itself. You know, rotation matrices has a, usually they look as, maybe I'll show you how rotation matrix looks because it's interesting. So let's stop sharing and I will show you how rotation matrix looks. Here, I think you can see it. No. Okay, I think you can see it. So the rotation matrix with angle theta counterclockwise look like this: cosinus theta, cosinus theta, sinus theta, and minus sinus theta. Okay, so you could also apply 120 degrees like in the first question and get this value with radians to this and get the matrix, and then let's try to calculate, I don't know, eigenvalues and things like this. But we didn't get into this, but this is the rotation matrix for counterclockwise. Now the rotation matrix for clockwise, please. So if we look on this, you can see how it changed. So cosinus and cosinus theta stay right over here, and minus sinus theta and sinus theta. Oh no, you just plug in minus. I see. Okay, but is there a matrix in general form for a clockwise direction rotation? It's just interesting if we can. No, I think there is no, because it needs to. Okay, so just plug in minus theta and use the identities of trigonometry and getting, instead of minus theta sinus theta here, minus sinus theta here, but this quite. Okay. Okay, this is it about the exercises on the rotation matrices. We saw 2 exercises, 2 questions, and we just work with it. Thank you very much. If there are any mistakes or corrections, please tell me. I think that's enough for now, and that's it. Now we can stop share and say goodbye to you all.